We constantly hear in the news about crises and negotiations that drag on for decades, all because a country is trying to build a nuclear bomb. And of course, Iran is one of the most well-known examples. Since the 1990s, headlines keep repeating the same thing. Iran is getting close to a nuclear weapon. They've enriched uranium to over 60%. Yet, somehow, they still don't have a nuclear bomb. So that raises a simple question. Why does this take so long? If a country has unlimited funding, top scientists, and natural resources, why can't they just build a nuclear weapon in a few months or even a few years? The answer lies in one strange term you've probably heard before: uranium enrichment. Hello everyone, this is Files from the Ashes channel, but before we start, if you're new to the channel, don't forget to subscribe and turn on notifications so you never miss a video. At its core, building a nuclear weapon is about releasing an enormous amount of energy from the heart of an atom. To make that happen, we need a very special material with rare properties. That material is uranium. Now, here's the surprising part. Uranium isn't actually rare. It exists almost everywhere, in rocks, soil, even riverbeds. It's mined just like iron or copper. The ore is crushed into powder, treated with chemicals, and eventually turned into a yellowish substance known as yellow cake. But here's the problem. This isn't the kind of uranium that can explode. The real challenge isn't extracting uranium, it's processing it. Natural uranium is a mixture of different isotopes: uranium-238, about 99.3%, uranium-235, less than 1%. Uranium-238 is heavy and stable. It doesn't easily split, so it's basically useless for nuclear weapons. But uranium-235? That's the one we need. It's lighter, unstable, and capable of sustaining a chain reaction. That's what makes it valuable. So why not just extract more uranium and collect enough U-235? Because separating them is incredibly difficult. We're not separating two different substances like oil and water. We're separating the same element from itself. They look identical. They behave identically. The only difference is a tiny variation in mass, less than 1.5%. And that tiny difference is everything. To separate them, scientists use a method called centrifugation. Think of a washing machine during the spin cycle. Water gets pushed outward, clothes stay inside. Same idea, but much more extreme. There's just one issue. Uranium in solid or liquid form doesn't separate efficiently, so first it has to be converted into a gas. This involves complex chemical processes that turn yellow cake into a gas called uranium hexafluoride. This gas is the key to enrichment, but also a chemical nightmare. It's highly toxic and extremely corrosive. It can destroy most materials on contact. So before enrichment even begins, countries must build entire systems of specialized pipes, valves, and containers that can handle it. Once ready, the gas is fed into centrifuges, long cylinders spinning at insane speeds, up to 100,000 rotations per minute. At these speeds, heavier uranium-238 moves towards the outer wall. Lighter uranium-235 stays closer to the center. Sounds simple, right? Not even close. After one spin, the concentration barely changes, from less than 1% to maybe 2%. That's it. So the process has to be repeated, again and again, thousands of times. Centrifuges are connected in massive networks called cascades. Each one increases the concentration slightly, then passes it to the next. It's slow, it's complex, and it takes years. This entire process is what we call uranium enrichment. Now here's something important. Enrichment isn't just one level. It has stages. For nuclear power plants, about 3 to 5%. For research, around 20%. For nuclear weapons, over 90%. But here's the twist. The effort isn't evenly distributed. Getting from 1% to 20% takes about 90% of the total effort. Once you reach 20%, you're already most of the way there. That's why the world gets nervous when a country hits that level, because from that point, reaching weapons-grade material could take only weeks or months. But even then, having 90% enriched uranium doesn't mean you have a bomb, not even close. That's just the raw material. Turning it into a weapon is a completely different challenge. The uranium must be shaped into a precise spherical core, handled in specialized facilities to avoid radiation risks. But the hardest part, the detonation system. Uranium doesn't explode like gunpowder. It requires reaching something called a critical mass. A neutron hits an atom, splitting it. That releases energy and more neutrons. Those neutrons hit other atoms, and within a fraction of a second, a massive chain reaction occurs. For a nuclear explosion to happen, this process must occur perfectly, all at once. If we look at history, the fastest nuclear program ever was the American one during World War II. The Manhattan Project began seriously in 1942, and by July 1945, they had their first successful nuclear test, just 3 years. But that speed came at a cost. Over 130,000 people involved, a budget exceeding $2 billion at the time, the world's top scientists working together. Figures like Einstein, Niels Bohr, Oppenheimer, and Enrico Fermi. It wasn't just America, it was a global scientific effort driven by fear of Nazi Germany. The Soviet Union followed shortly after, building their bomb in about 6 years, but they had help through intelligence gathered from the Manhattan Project. Finally, it's worth noting uranium-235 isn't the only path to a nuclear weapon. There's also plutonium-239. Unlike uranium, plutonium isn't found in nature. It's created inside nuclear reactors from uranium-238. It doesn't require enrichment, but separating it chemically is extremely dangerous due to its intense radiation. Interestingly, the United States used both materials: the Hiroshima bomb, uranium; the Nagasaki bomb, plutonium; and later, the Soviets chose plutonium because it was faster than waiting for uranium enrichment. So, in the end, building a nuclear weapon isn't just about resources or intelligence. It's about mastering one of the most difficult industrial processes in human history, a process so slow, so precise, and so dangerous that even the most powerful nations can take decades to complete it.